Good, good evening, everyone. I hope you are able to see my screen and I am audible to you all, guys. You can write in chat box or you can unmute yourself and you can say. We will wait for few minutes. If someone joins, then we will proceed, or else we will proceed with. So, good evening, everyone, and welcome to the second week of this problem solving session on the subject that is industrial wastewater treatment. The course instructor for this subject is Professor Alok Sinha and Professor S.K. Gupta from IIT ISM Dhanbad. And my name is Maniratnam Prakash, and I am from IIT Kanpur. And I every I will be conducting this session. So this thing you already, those who have joined for the first time and those who have not joined last time, we meet every Tuesday. You get notification for this thing prior, one day prior to this original meeting. Timing is this, and the Google link has been also shared with you, and the recording of this session is available on YouTube channel. I think the link for which has been already shared with you. If not, then you can. I will share at the end of the discussion. And if you think if you have missed out anything during the session, you can just come back and check it. So generally, like I have been taking this session from last 1.5 years. So generally, what my experience is that first I discuss some recap all those things which are there in the lecture, and based on those we solve some problem. But last week, some of you, many people suggested that there is no need of recap of whatever has been already taught, so directly I start with the question answer. So this week we will be doing that only. That we will be next slide is of question answer. I will be giving some questions. First you attempt it, and then based on your attempt we will proceed with the its solution. And in between, if you think that this topic is not covered, I think everything is covered, sorry, everything is covered. If you have any doubt in any particular session or any particular topic, then we can discuss it. I have lecture materials, and we will be discussing those lecture we will be discussing those topics. Okay, from last week. If anyone have any kind of doubt, then they can ask now, or we will proceed with big two lectures. Anyone have any kind of doubt that was discussed in week first? In week first we have basic discussion about industrial wastewater, what is industrial wastewater, then different management, then we discuss about different sorts of industrial waste, and we also went through treatment unit where equalization, we also look into something called equalization tank, and neutralization and all these things. Anyone have any kind of doubt, you can just write in chat box also. Chat box is always open. You can see chat box. I have opened the chat box. If you write type anything, I can see it. If you are, yes, so you are, sorry. Okay, see, if you do not reply anything, I will proceed. Miss, I will assume that you are okay with it, and I will proceed further. Okay, if you have any kind of doubt, any kind of question, just write in chat box. Okay, I think no one have any kind of doubt. Then I will proceed. In big two major two thing was discussed, that is ion exchange process and adsorption process. Both are treatment process. Like there are several treatment process. If you want to treat something, then there are several treatment process that we will be looking into. We will be looking in the in upcoming lectures. But in this lecture, these two was discuss ion exchange in simple way. If we want to say in simple way, then we have polluted water, yeah, contaminated water, that say we have sea. Then this contaminated water is passed through one resin. Okay, now this resin contains some kind of ions opposite to our contaminant, yeah, similar to our contaminant, and that is not that is not causing any kind of secondary pollution. What will happen, that there will be uh, suppose this resin contain R, okay na, R as a maybe anion or cation. So what will happen, that this contaminant will get exchanged, and this is simple ion exchange process. And then we have adsorption process. In adsorption process, we have some kind of solid, and suppose we have contaminated water, we put those solid in the contaminated water, and ions get adsorbed on the surface of that adsorbent. Remember, actually there is two things, but in your part only one thing is discussed, that is adsorption, but there is another process, that is absorption. Okay now, so there is difference between, I'm not going to discuss what is adsorption and absorption, but you should know that there are two things, adsorption and absorption. Okay, so in in this system, these two, there are different adsorbents for removal of different contaminant. We use different type of adsorbents. Okay, I hope these were just a brief things, not a detailed thing. Okay, so from next slide, I am going to give you some questions, and I have assumed that you have gone through the video lecture. See, the point of this problem solving session is that you will be able to like solve the problem if and only if what do I call, if you have watched the video lecture. Miss, if you have not watched the video lecture and you have come here just for to check the answer that might be in your problem solving session, then I don't think this is the purpose of this session. And I hope what I am saying, I hope you are getting what I am saying. So the first question is based on adsorption. I will give 1 minute for each and everyone to respond to this question. Like, what is their answer? Which of the following factors affect the process of adsorption? As it is asking which of the following factors, then it is a multiple correct question. One or more than one option might be correct. So please read the question and try to answer it. It's 6 9. I will wait for 6 10, and then I will be start. I will discuss its solution. Anyone with any answer? So this is not. I don't know. Okay. Then there are several options like the first option is solubility of absorbate. We have said that absorbate is the solid which will treat our contaminant, that where on this solid this contaminant will get absorbed. The first option is solubility of adsorbate, and this is correct option. This indeed it affect the adsorption. How? If the absorbate is highly soluble, that is solvent, it tends to remain in dissolve rather than getting adsorbed on the surface of absorbent. Okay, sorry, I initially see there is two thing: adsorbent and absorbate. Bait and vent. Vent is absorbent is the solid where this absorbent will get absorbed. Okay, now so this is our contaminant. Suppose in water we have, suppose we have fluoride in water and we want to treat fluoride. Then fluoride will be absorbent, and suppose if we are using aluminium for removing fluoride, then aluminium for removing fluoride, then aluminium will be absorbent. I hope this is clear to you. Now what will happen that if the absorbate is highly soluble in the solvent, that is water, it tends to remain dissolved rather than getting absorbed on the surface of the absorbent. Now we want something. Now suppose it's simple. Like if we have added some solid, then whatever contaminant is there, it should have some kind of attraction or affinity toward this solid. If there is no affinity toward that solid, then it will remain in water as it is. It will won't get adsorbed. If the adsorbate is less soluble, absorption is generally more favorable because molecular prefer to move from solution phase to solid phase. Now this is another phase, like it is not so dissolve in the dissolved form. Then what will happen that there are high chances that that contaminant will get absorbed on the surface of this absorbent. Example: gases with low solubility get absorbed more on the activated carbon compared to high soluble gases like ammonia. So this is example of gas, but I am also giving example of few of some industrial contaminants such as suppose if we have uranium in our water. Uranium, no, let's not consider about uranium. If we consider arsenic, there is a great many there is a arsenic, and if we want to treat arsenic, then we generally add iron. And what happened that this iron will get absorbed on the surface of this arsenic will get absorbed on the surface of iron. Now what will happen that if the and its effect, it get absorbed because this arsenic has affinity toward this iron surface. But if there is no affinity and some other solid is added, then arsenic tends to remain in the dissolved form only. So the correct one of the answer is A. Look at the second option. Concentration of absorbate. Higher the concentration of absorbate in the surrounding phase increases the probability of adsorption. Obviously, in water, suppose there is a more fluoride, then more adsorption will happen, and if the fluoride concentration is very less, then less adsorption will happen. Then of course this is also correct answer. Higher concentration of absorbent in the surrounding increase the probability of adsorption on the absorbed surface. This is another thing that we will discuss in the upcoming questions. Okay, now Then surface of the absorbent. Now they are talking about the surface of the absorbent. This is the most important factor. Remember what happened that in adsorption, generally what happened that there is surface area. Surface area. More the surface area, more the adsorption. Now if the means surface area is like this is a flat surface and this area. Now remember if there is a more surface area, then what will happen that if any contaminant will form a better bond here, it's not like covalent bond or ionic bond. It's simple attract electrostatic bond or surface complexation and all these things. So what will happen that more the surface area, the chances of adsorption is more. Indeed, miss many book have reported that like I was saying about this fluoride adsorption of alumina. Okay, now that is Al2 O3. Okay, now so what happened that if you go in the market and if you take this Al2O3, it will have a surface area of only 10 meter square per 10 meter a square per gram. Okay, now what will happen, what people do that they heat this alumina, will take it from market, they heat it and they make it, they call it activated alumina. Okay, now what will happen that it has several form, that alpha form, beta form. Now say suppose we have alpha Al2O3. Depending upon how you are treat, means how much you are heating it, we get alpha beta and all these things. So what happened that in this case, this the when it is thermally activated, that is known as activated alumina, the surface area increases to 200 meter square. Okay, so now we so now here the efficiency is around 10%, but around 10 to 20%, but in this case the efficiency is around 90%. Okay, so indeed the surface area of the adsorbent also affect adsorption. The last option is lyophilic and lyophobic. Lyophilic and phobic means fear and attraction. This we all know. Lyophilic means solvent attraction. Substances have a lower tendency to absorb because they prefer to stay in dissolve. Now suppose we have, suppose again this is like again we have some contaminant which like to stay in water, means it is lyophilic. And if suppose some solid is added to remove that thing, then what will happen that it won't get attracted toward this surface, but it will remain on, hmm, it will remain in the dissolved form. And another cause, another case, if it is lyophobic but it is not liking the water or maybe any other kind of solvent, and if we add the solid, then there are high chances that absorption may occur. So the final answer is all A, B, C, D are correct. I hope this is clear to you. I don't know, anyone is not speaking anything. This is a problem. Like if you won't speak anything, then it will be like I'm just delivering something, whether you are understanding anything or you're not, I don't know. I hope you have got my point. Now this is another question, like Freundlich isotherm. Again, if you have gone through the, see, okay, I understand that no one is going to answer, then I will just move forward. So see what happened that there is something called CS, that is absorption capacity. Okay, and it has some formula. Then we have concentration. Now what happened that the sorption density. Now what happened that if the sorption density is proportional to the concentration. Okay, then it is known as linear isotherm. I hope you are, everyone is aware. Anyone? Any doubt with what is this isotherm, adsorption isotherm? No response. Then I am assuming that you know. Okay, no response means whatever I have assumed, and I have assumed that you know, then I will move forward. Then the formula is given this. But when this when the sorption density is not directly proportional, but it depends upon some constant and the concentration ki power n, then we get this type of curve, and that is known as Freundlich isotherm. Okay, now. And then third type of isotherm is langular isotherm. So if you are someone is, I think someone has joined miss here, someone is have written that he is or he or she is some kind of researcher. Then if they if hmm, if they are if that person is working on contaminant removal, then they have to deal with this kind of isotherm. We perform experiment and we want to know that which kind of isotherms our uh, our experiment is following. So this helps to uh, understand how adsorption is occurring. Okay, na. So these are simple formula. CS in linear isotherm we have CS is equal to K into CW. Then in frontlet we have CS is equal to KF CW ki power n. And then in Langmuir we have CS is equal to CS max. There will be every isotherm what will happen that mhm, every system, every solid will have a maximum capacity. Then that is maximum density into KL is a constant, and then we have CW that is concentration. Again, it will be multiplied. Okay, na. So this is this question is very easy, and the correct answer is B. That is x ki power m kf ce 1 ki power n. It's slightly different because it has been written in different form. Here x is the mass of absorbate. X by m, sorry, not here only the formula. This see here I have written n, then n vary between n will be equal to 1, or it will be greater than 1, or it will be less than 1, but here it is 1 by n, and then only what will happen that the unit of kf will change. Okay, na. Everything will be changed, but the unit of kf will be changed. And you can see that 1 by n lies between uh, 1 by n lies between 0 to 1. Okay, na. It's same, but it's written in different form. Okay, na. Here the unit of, I don't see the unit of f is written, but depending upon the question you will be get like what kind of, and several book follow different technique. Okay, na. So if you want to read more about this isotherm, I will suggest one book, that is Water Chemistry by Benjamin. If you are interested to read about more things, I will just suggest one book. Let me open that book. This book, this has explained this adsorption process in very detailed way. And if you are environmental engineer, and if you want to be environmental engineer, then if you go to any IIT, most of places they will refer you this book. If you are, if, I think chapter number 7 deals with adsorption, no, solving software titration, gas liquid redox. This adsorption reaction, chapter number 13. Okay, na. I will suggest you. This is a good book, highly recommended. If you want to if you want to learn more about this adsorption process, just go through this book. Okay. See, for in my MTech also, in my PhD also, during my work also, I follow this book whenever I come to any problem. Okay, here you can see how adsorption occurs in how different in different condition. You can see they have say they have we have surface area, there will be molecule absorbate will be there and it will get absorbed on the surface. Okay, this type of reaction is there. Industrially, how industrial in the see in industry in industry this concept is also used. So again, you can this is available on the net, you can download it, you can take a screenshot shot. Water chemistry by Mark M Benjamin. Coming back to our discussion, third question is carbon usage rate is defined as. Again, this is a theory part. Again, if you have any kind of doubt, you can write in chat box or you can just. If you are someone is waiting that at the end of the session I will ask some question, at the end of the session we don't might not have any time. Okay, now because I will end the session at 8 p.m. maximum. I can go for 8:05. So don't wait for the session to end. You can just ask here. I am giving you full independence. Do it's hmm. Carbon usage rate is defined as okay now the amount of GSA required per unit volume, amount of absorbate required per weight of the GSA throughout the volume of water per unit weight of GSA. GSA is be defined as granular activated carbon. You say granular activated carbon. GSA is defined as, and in technical term or in industry, this is very generally used. Wherever you will see carbon, they talk about carbon. They will talk about this GSE and GSE and related to that we define carbon usage rate, that is CUR, and it is generally defined as mass of granular activated carbon used divided by volume of water treated. Okay na, so the correct answer will be A. It is expressed in milligram per liter or kg per meter cube and represent the amount of GSC required per unit volume of water treated. And then we have so the first option was correct. Second option they were saying that amount of absorbent removed per unit weight of GSA. So that is not that is not CUR. That is another thing that refer to absorption capacity, CS. Remember we have shown you this formula CS. This CS is known as absorption capacity. It has different term: absorption capacity, absorption density. You can say anything. To get more clarification why it is called sorption density, sorption capacity, you can always refer to that. You can always go and read that book. Okay na. So x is the amount of absorbent removed and mass is m is the mass of absorbent. Here the m here the absorbent is GSE, that is granular activated carbon. Okay, so that's why this was incorrect. Second is throughout the volume of, I think is written wrong. Throughput volume of the, sorry. Uh, Second option is this represent the sir, can you solve one question of ion exchange? Yeah, yes, I will solve that. Means okay, I will go to next. I will go to that question only after this question. Okay, let me finish this thing. Okay. Uh, this represent and so invalid, then our correct answer is A. So in your there is one this question, I think you are talking about this question. Where did it go? So that nitrate question, that 4.5 molar of an ion is there, 4.5 millimolar of cation. I hope you are talking about that question. And we have to remove nitrate with the help by exchanging chloride. So see, that question has been directly taken from your lecture. First of all, I want to say that thing. Just 1 minute. System. So are you talking about this question? Are you able to see my screen? Hmm. Are you talking about this question? That ion exchange is implied for nitrate removal in absence of sulfate water. Okay, the objective is to eliminate the nitrate from treated wastewater sample with a specified composition. For illustrative purpose, assume the utilization of conventional ion exchange regime. Calculate the maximum volume of the water that can be treated per using. So this question is directly from your this lecture notes. Okay, now for this solving this question, you have to know two three things. That is, first we have to find the fraction of adsorbent that is being that has to be removed, and that is given by this equation. Okay, now there is uh, there is a proof that how there is means like not proof but yes, sorry, proof, there is a proof also, that suppose here we can see that uh, ra that is our resin and B is our contaminant, and we have to treat B. Okay, na in means B is pollutant, and suppose here in your question B is nitrate and A is chloride. You have to remove, you have to treat this nitrate. Sorry, let me just see, am I saying correctly? Huh, we have to remove nitrate. Okay, nitrates, and with the help of chloride, means chloride will this is a concept of ion exchange, means chloride will be replaced by nitrate. Okay, na then we know that reaction the this xa, that is mole of this, will be given by um, uh, this xan is the equivalent fraction of a and b in the solution, and as both are fraction, though sum of this fraction will be equal to 1, that is xa plus xb is equal to 1, and then xa will be given by the xa. Now xa is the equivalent fraction of a in the resin. Okay, now so what will happen, that whatever the and see, this is a fraction in the region, and that will be given by Ra minus. You can see that total equivalent total cationic concentration in the region is if C bar, then the fraction will be given by this equation. Then Xa bar plus Xb bar will be also 1, as both are fraction. Okay, now then we can substitute this thing. We know that K reaction constant will be this concentration of this into this divided by concentration of this into this. Okay, na what? Okay, na miss, you have question, yeah, are you saying thing anything? Then sorry. Hmm. See, now we have this thing a plus into r, uh, we have this reaction constant. Okay, I don't know why you said okay na. Hmm. Then I was saying about this fraction, that in resin and in contaminant the fraction will be equal. The sum of fraction of for each terms will be 1. That is we have written here. Now we know the reaction constant will be given by this term, that is a into this resin b plus divided by this thing. Okay, if we substitute the value here, if you if you if you carefully look here, then if you can substitute the value of a plus, that is a solid, in this equation, that will be xa into c, xa into c. And similarly for b solid you can put this value, and similarly in the place of ra plus ra dash a plus you can put this xa bar, and in place of this thing you can place this thing, and finally you will get this expression. You can perform this task and you will be getting this expression, that is xa bar b into xa xb plus x bar for b, xa, then xa bar for a, and then xb. And here then for and generally our aim is to find the fraction of fraction of contaminant that has to be removed. Now suppose here our contaminant was b, then we have to find the concentration, we have to find the fraction that will be removed, and that will be given, you can put the value here again, and you will be finding that the fraction of b that will be removed, that or that will be in the resin, will be given by this x bar b plus 1 minus x b bar, then k into xb, the concentration in water minus, sorry, not concentration but fraction in simple thing. So here you can see the solution also. Here you have been given the different concentration. Okay, that is calcium is 1 millimolar, magnesium is 1 millimolar, sodium is 2.5, cation is 4.5, chloride is 3, sulfate is 0, and nitrate is 1.5. So total equal amount of cation and anions is there. Okay, then we know that in equilibrium condition what will happen, that whatever the, suppose we are treating our contaminant with some kind of resin. So after resin has get saturated or it has achieved equilibrium, whatever this I am adding in the water, the in the outlet we will have same concentration. Okay, now the first we will find the fraction of contaminant in our water. Total concentration is 4.5 and nitrate concentration is 1.5. The fraction will be 0.3. And we have seen that to find the concentration in resin, that how much contaminant has went to the resin, we will be using this formula, and you have already seen the formula for how we have get this formula. Okay, then that will be given by x bar 1 minus x bar into 4. 4 is our k value, it is given in the question. Okay, into friction in water, 1 minus friction in water. From here we can found out that the nitrate which will get absorbed on the resin, will get attached on the resin, will be only 0.66, that is 66%. So 66% of the exchange site on the resin can be used for removal of the nitrate. Okay, so limiting operation. Now they have also given in the question that this exchange capacity is only 1.3 equivalent per liter. Okay, now whatever we are adding, only 1.63 equivalent per liter will be get exchanged. So we know the efficiency of fraction, that is 0.66, or we can say the 66%. So limiting operation we will multiply it with 1.3, then we will be getting it, the treatment or operating capacity will be 1.6 into 0.66, that is 0.86 equivalent liter of resin. Now we have to calculate the volume. Okay, now the volume of the water that can be treated during the service is equal to nitrate removal capacity of the resin divided by the nitrate solution, means nitrate solution. Now we know that this is operating capacity, that per liter only 6.6 equivalent means for per liter of resin only zero point 0.6 equivalent can be treated. Now from this we have to find out the volume. Then we can use the what is the what is the then we can use this operating capacity, that is 0.66. And we know that in our water we have only 1.5 concentration, 1.5 equivalent milli equivalent per liter. Then here we have put those things, 0.6 equivalent, and as it was in milli equivalent, the 1.5 into 10 to the power minus 3 equivalent. Then we finally get this answer of 573 liter of water per liter of resin. Means 1 liter of resin, per liter of resin can remove 573 liter of water. Sorry, treat 573 of water. I hope so. So overall concept was, the first you should know this concept, that how much resin is getting adsorbed, and based on that you will be finding the operating capacity, and based on the operating capacity you can find out the volume of water treated. Any doubt? I hope you have understood, Astha. Astha. Any doubt? Okay, now if you have understood, then solve this question. If you have understood, I will ask you to solve this. Now they have, see, first take a screenshot of this. These are equation. Here sulfate is 0. Okay na? Here sulfate is 0. But in this question they are saying that we have sulfate also, that is 3 millimolar equivalent. And nitrate, here what now they are saying that chloride is 0. See here in this question sulfate was 0, but in this question we have now the only thing is that in this question our, see in this question only simple question is there. Here we have nitrate. In previous question here B was nitrate and A was chloride, but in this question B is still nitrate but A is sulfate, and they have given you the given you the data of sulfate. Here the this K value is 0.04, and for this will be always constant. The exchange capacity will be 1.3 equivalent per liter only. Okay na? So I want everyone to solve it. I have explained you in a proper way. I will request you to solve it. I am coming in 1 minute. Please, it's very simple. If you have understood that process, whatever I have explained, only you have to do find the fraction of nitrate that that can be removed in this, and you have to use this formula. You have to use this formula. Once you get the fraction, then you know the capacity, that is 1.3. Then sorry, exchange capacity. Then you can find the operation. Then you will be able to find this operating capacity. Once operating capacity is known, you can divide it by volume of. I am also giving you the options. 20 liter water, 40, 60 or 80. In this question there was no use of any that calcium data, magnesium data, because we are not treating. Please, any answer? I'm giving you, it's 45. I will wait for, I will wait till 47. But first tell me, are you guys solving or not? Yeah, see, if I am waiting, then it's just a wastage of time. Just tell me, sir, please proceed. I will proceed. There is no need to waste time. We can have discussion. Are you solving anyone? I think no one is solving. Am I correct? Basant Kumar, are you solving? Astha, if you have understood, are you solving it? Then we have Prabhu. Lete Basa. Did anyone get any answer? No response. I don't know what to say. Again, here you can see that this first we find out the friction, that is 0.67. Okay. Then we find out this x bar. Here it will be x bar, not x. There is printing mistake. It will be x bar, that is 0.93. Then we can see I'm traveling. Oh, it's okay. The relative amount of nitrate convection that in equilibrium with nitrate. Again, it was very simple question. It is 93% is being removed. Then we can, here we can see that here in case in here we have tried to solve in a opposite way, like, because here you can see the value of k is given between chloride and sulfate. So there will be a, the trick was that in case the k value was given for chloride to nitrate. So here the equation was simple. Equation was simple. Here it was chloride. Here it was nitrate, But when now the in your given question the K value is given for nitrate to sulfate, okay na, then if you follow this process, then you will get wrong answer, okay na. First you have to find thing which we know that fraction summation of fraction will be 1. This thing we know x the fraction in resin and fraction in water, in both case the fraction will be 1. But in this question what we are doing that as K is given for from nitrate to sulfate, then we have to find the fraction of, first we have to find the resin fraction of sulfate, okay na. Then here you can see that they have found it for sulfate, and as for sulfate it's 0.97. Then and we know the summation is 1, then the fraction of nitrate will be 7% only, okay. 1 7%, then we know the limiting capacity, we know the capacity that is 1.3. From there we will find the operating capacity. Once we know the operating capacity, then we can find out the volume, and the volume come out to be 60 liter of water per liter of resin. Anyone any kind of doubt in this question? What this was little not tricky question, it was just presence of mind. If someone started to solve based on the solution, they started to do same thing without looking that whether k is for k here, k is for which reaction. That's why it is always recommended look have basics. Once you know the basic, here we can see the basic that resin will contaminant will be attached to this thing, what to be called, contaminant will be on the reactant part, contaminant will be anole, and the resin will contain some kind of ion which is ready for exchange. And on other hand, on the product side we will have contaminant with this reactant part, and then we have, and we can we always look that k is for a and b, then this equation is always for b, okay na. And there was another method that if k is for forward reaction, if k is 4, then for backward reaction the k will be in the reverse order, that is 1 by 4. Another method was that also, that if it is 0.04, then someone can reverse it, that it 1 by 0.04, that will be around 25. Then that will be for from sulfate to nitrate, and it will convey that nitrate is getting here, it is, if without any context, if someone look at this expression, they will say that nitrate is replacing sulfate. Sorry, sulfate is here, if someone see it, it will say that sulfate is contaminant and nitrate is attached with resin, but that is not the case. I am giving, I think I am explaining, I don't know why you guys are not responding, but I think I am explaining in a good way. We have another question. In adsorption study, 2 gram of GAC, that is granulated activated carbon, was added in 100 ml of water containing TOC concentration of 10 milligram per liter. The equilibrium concentration of TOC after adsorption was found to be 1 milligram per liter. Find out how much TOC in the mg was absorbed per gram of GAC, that is granulated. Can anyone say this question is very simple question? This is the most simple question. You won't. You might get this question in your assessment, but never expect this kind of question in your exam, because these are very easy. Just value substitution question. If you know the formula, what is the formula for equilibrium concentration? What is the formula? There is only single formula in adsorption. That formula is modified left or right to get some different formula, but overall there is single formula. So see, the equation is very, the formula to solve this equation is very simple. Again, this has been, this is in your lecture also. If you look into the adsorption part, hmm, this is the equation, isotherm adsorption isotherm equation, that's QE. Q is adsorbent phase concentration in equilibrium, after equilibrium, okay na. It will be initial concentration of absorbate, that is a contaminant, minus equilibrium concentration of absorbate after absorption has occurred, into volume of the liquid and divided by mass of the absorbent. Here in your question everything is given to you, how much absorbent has been added, how much water is there, how much initial concentration is there, how much final concentration is there. Okay, here you can see it here. Q is equal to Ci initial concentration minus equilibrium concentration into volume by M. Q is, we have to find, Ci is initial concentration 10 gram per liter, milligram per liter. C is 1 milligram per liter. V is the volume of the wastewater, that is 0.1 liter, and M is the mass of GC, that is 2. We will find out C minus Ca. We will convert into, and you can find out, if we substitute, just substitute all the value, you will get the Q is equal to 0.45 milligram per gram. Remember the unit, the answer is 0.45 milligram, that is this one. So remember the unit, the unit is, already we have to find milligram per in gram, okay na. So that will, the final answer will be 0.45, that is C. Again a question related to ion exchange. This is theoretical question, and this is like, if you have paid little bit attention in your video lecture, you might be able to answer it. Ion exchange process is used for removal of hardness, heavy metals, TDS, nitrogen, that is ammonia, and nitrate. NH, actually it should be NH4 plus and NO3 minus, but they have not written minus and plus. But it, NH4 plus is ammonium and NO3 minus is nitrate. Again, I don't know why no one is responding. So, so this is the basic definition of ion exchange. Ion exchange is a process widely used for removal of various contaminants from by exchanging unwanted ions with more desirable ones using ion exchange regime. Let's analyze each option. Hardness is only due to calcium and magnesium. I hope this is very clear to you. Yes, it is being removed by ion exchange. Cation exchange replace calcium and magnesium with ions such as sodium, hydrogen, softening the water, and this is a simple reaction. Okay, na. The reagent which contain ammonium is known as zeolite. I don't recall, but I request you to, sir, go and zeolite, Zeolite. Okay na, Te. And arrangement is very simple. What happened that we have a system like this. We have a system like this. This part is filled with sodium resin, water is passed through it, and what happened that calcium, magnesium, calcium, if your water contain high amount of calcium and magnesium, it will be exchanged like this resin, this sodium will be replaced and calcium will get attached, and we will have this, what do we call, this hardness can be removed. Okay na. Then yes, A option is correct. Then we have heavy metals. Yes, heavy metals are very commonly used. Happy again here also this same kind of cationic exchange happens. Heavy metals are replaced by sodium or H plus using cation exchange resins, widely used in wastewater treatment to remove toxic metal. TDS, yes, remove TDS. TDS. See, you have to understand what is this TDS. TDS is dissolved solid. We are saying solids, and it is due to dissolved solids. And dissolved solids contain sodium, calcium, magnesium. Okay, na. So so you have to, it's not like we are removing solid, it is already dissolved TDS is due to presence of different ions. Okay now, it means there is a famous question, if someone is preparing for gate, and if you are solving previous year question, then you might have come to this question, what does this TDS represent. Then there is option conductivity. I hope, if someone is preparing for GATE examination. Hmm. Yes, remove by both cation and anion exchange reagent can be used to remove tedious component like sodium, chloride, sulfate, etc. Demineralization process using a strong acid and strong base are almost remove all the ion effectively. Obviously, if all the ions which is there it is removed, then TDS will get reduced. Okay. Nitrogen, and yes, we have already seen the example here with the help of chloride ion we can exchange we can remove nitrate. Okay now. Remove using a cation exchange resin, removed using anion exchange resin. Using drinking water treatment to remove excessive nitrates. So the correct answer is D, that is ABCD. Because here see the question was like this. So the correct answer will be D. Now comes the sixth question. This is theoretical question. Weak acid cation exchange resin consists of the following functional group. If you have gone through the lectures, there means like you have to, actually there is science behind it, that to remove which to remove some particular group of acid or base, that remove particular amount of which kind of resin we should use. That I am not going to discuss here, and I have also very less idea. But here you can see, here you can like try to answer it if you have. I will just answer the question. The correct answer is carboxylic acid. Weak acid, that is W exchange carrageenes, contain carboxylic acid functional group that help in cation exchange by donating H plus. These resin primarily remove the alkaline metals such as calcium and magnesium and other divalent cation from water. Okay, then see, if you look into the other option, that is sulfonic group SO3H. Incorrect. Sulfonic group are found in a strong acid cation, that is acid exchange, not in weak acid. So, for a strong acid we use sulfonic acid, sulfonic group. Okay. SAC exchange H plus from, again here there will be, see, if you go through the lecture, a table has been made like for which kind of, hmm, for which kind of reagent, which kind of pollutant we can use, which kind of reagents. Okay. Similarly, carboxylic acid, I have already said that it can work. Then we have ammonium group. Ammonium, quarterly ammonia present in strong reaction which remove. See, for fluoride also, there should be fluoride also. For fluoride also we use ammonium based, what do we call, resin. But like in case of fluoride treatment, we use ammonium waste, that is NH4 Cl. Okay na. And when fluoride water is passed through it, it removes chloride, and we get fluoride treated water. Again, this is not answer. Correct answer is B, carboxylic group. Then This is a theoretical question. Two monovalent cations A and B are treated by cation exchange resin separately in a dilute solution of water. Cation A is have higher selectivity coefficient in comparison to B. Which of the statement is true at equilibrium condition? Okay, now just go through this equation. Discard. Oh, sorry. Just don't look at the answer. Hmm. What I was saying that to answer this question, this is like very good use of what do we call? You have to use this concept. Now they are asking to question is very simple. I have taken question from this thing. Huh. Question is very simple. That we have two monovalent ion in direct matter. Cation A have higher selectivity coefficient. Means K is high for A as compared to B. Okay na? Cation A have higher selectivity coefficient. Use this formula like then if I have high selective coefficient, which of the following is true at the equilibrium condition? Then which of the following will have a hmm. So the distribution curve we use for selectivity coefficient, concentration is reagent distribution. So use this formula. Like see, use this curve, not formula. Distribution curve. See, if the concentration in resin is very high, suppose this is 0.8, okay na, and the concentration of at concentration in solution is very low, then it will have high. These are selectivity coefficient, that is 0.1, 0.2, 2, 5, and 50. Now they are saying that as two there are two ions and A has higher uh, A has uh, higher selectivity coefficient. Okay, then which of the following uh, i- uh, is true at equilibrium? That A will have higher concentration in solution as compared to B, or B will have higher concentration in solution as compared to A. Okay now, so you can see that when in which condition we can say that A which like if the concentration in resin is very high, then we will see we can comment that yes, our treatment has occurred and the concentration in water will be very low. Okay now, miss in if we look at this in this curve, suppose what happened that we treated something and we found out the concentration in resin is very high and the but concentration in solution is very low. If that is the case, then we can see that most of the solution which was there in the uh, which was there in the water, that contaminant has been treated, so that concentration of that contaminant would be very low. But when the selectivity coefficient is very low, say 0.1, in this case what we are seeing that uh, uh, the treatment is not so good, means exchange has not happened. Even though we have passed some solid, we have passed our polluted water, what has happened that there has been not proper exchange, and so the concentration of contaminant in the water will be still high after passing it through the resin also. So as here it is saying that A has higher selectivity, means a proper ion exchange has occurred. But if we talked about B, no proper exchange has occurred. So what will happen that B will have higher concentration in the solution, or A will have. So the correct answer will be B. I hope you are able to understand what I am saying. Higher higher selectivity coefficient means good treatment. Its concentration will be low in the water, and then lower selectivity coefficient means poor ion exchange, means less treatment has occurred. Okay. This is incorrect. Since cation A has more selectivity coefficient, it is more attracted to the resins. Okay, like just simple. Remember, more selectivity, more efficiency of treatment is good. If the more efficiency is there, then in treated water we will have less concentration. Therefore, the less of A will remain in the solution and more of B will absorbed by the resin. As a result, the concentration of A in the solution will lower than that of B. Then we have second option. B will. This is correct since cation A has lower selectivity. The resin has a weaker affinity for A. Consequently, the more of B will remain in the solution, leading to the higher concentration of B compared to A. So the correct answer is B. Both will have equal concentration. Both will have same concentration. This is correct. Incorrect because the concentration of the ions is dependent upon the selectivity of the reagents. I hope I have explained you are able to understand it. This D option is incorrect. Then last question of problem solving. Then we will have normal discussion and we will see some other example if we will see what we will do. Hmm. The question number 8, that is in ion exchange method was employed to soften 200 liter of water to regenerate the exhausted resin. 250 liter of zero point 0.1 normal HCl and 250 liter of zero point 0.1 normal NaOH was required. The hardness of the water sample. So what have I will give you the context. What has happened? That there was one resin, and as we are talking about hardness, then it must have calcium and magnesium. Okay, na calcium and magnesium. So calcium and magnesium contaminated water is passed, and what happened that obviously there will be exchange, and this calcium and magnesium will get trapped here in this resin. Now we want to use this resin again for further treatment. Then we have to clean this resin, or the technical term is regenerate. To regenerate, we will be using calcium and magnesium. Sorry, we will be using acid and then base. Okay, na. There is there means like there is I won't be able to explain why HCl and NOH has been used, but there is a like there is scientific reason why HCl and NOH has been used. Okay, now. So I will request you to go and check why these HCl and NOH was used. Okay. Hmm. So what will happen that now as this much amount of this much amount of acid and base has been used, means with the help of this information we can find out how much calcium and magnesium has been removed, and that calcium and magnesium must give the amount of hardness present in the our initial water. Okay, now. So anyone want to solve it? Okay, I will proceed with the solution. So, like, first we have to calculate the equivalent of HCl, and NOH used. Okay, na. So the equivalent is normality into volume, and here it is saying that 0.1, then 0.1 and 250 liter, then 25 equivalent of NOH was used. Similarly, the sorry HCl was used. Similarly, the equivalent of NOH was similarly the equivalent of NOH. I hope you are getting this concept of equivalent and all these things. There are many things which I assume that you guys know. That's why I'm not discussing. Okay, na? What is this equivalent? How? What is this normality? I hope. I don't know. Yeah. See, if you have doubt in these terms, technical terms also, what is this equivalent? What is this? Now we know the equivalent of HCl and NaOH. Since both HCl and NaOH react with hardness in a 1:1 ratio, the number of equivalent of hardness ions is also 25 equivalents. Okay, na? See, this is like known things that NaOH and HCl react with hardness ion, that is calcium and magnesium, in 1:1 ratio. Okay, na? So we know the equivalent of this HCl and NaOH. So the equivalent of hardness will be also 25 ions. Now we know the equivalent of hardness. Then we can multiply it by equivalent weight, and equivalent weight of calcium is normal weight is 100 gram per mole, and when we multiply it by 2, because it has a valency of 2, that is Ca2 plus, then its equivalent weight is 100 divided by 2, that is 50. Then that is, then we will have the mass of carbonate as 1 to 50 gram. Okay. Then finally we have to convert this mass of CaCO2 in the hardness as part per million, or ppm, or we can say milligram per liter also. Then hardness will be mass of CaCO3 divided by volume of water into 100, because we have to convert into part per million. Okay, na? And sorry, we have to this part per million is milligram per liter. Okay, na? And we know the concentration in gram. So this gram, that is 1250, has been multiplied it by 100. Then volume of the water is given to 200 liter. Then the final hardness will be 625 ppm. Any doubt? Anyone, any doubt in this question? The answer to this question will be 625 milligram per liter as CaCO3, because we have converted our hardness in the terms of CaCO3. And remember, unit of hardness, unit of alkalinity is milligram per liter. So it is written as ppm, but it will be final. It will be written as 220 to 625 milligram per liter. Okay, na? So these were all 10 question, 8 question. This thing here, and 2 question I have already discussed on the in the PDF. Okay. So I will just request you to ask some specific doubt. If you have any kind of a specific doubt, mm, you can ask. Anyone have any kind of a specific doubt in from this? All, did all of you get this? Have access to this video lecture? Sorry, lecture material. Hope everyone has the access to this material. Yes, sir. Then any specific doubt to anyone, or should I give more? See, I have some questions If you want to solve, then I can show it to you and then you can solve it. We have around 30 to 40 minutes. Okay, I don't know. Please, anyone, how, miss, like, what? Okay, I will give you some questions, some more question. I will just show you how it has been done. For few minutes, I will turn off the presentation mode. Then I will reopen the presentation. Just give me few minutes. Just wait for 1 minute. I am showing you some question. Then hmm. So see, this question is related to friendly isotherm. Okay, now I hope you are able to see my. Just I can do one thing. I can paste it here. See, this question will take few minutes. So I want everyone to solve. Miss those who I know Prabhu cannot solve, but others, those who were actively participating, just go through this question. Now, the question is very simple that a water contains 10 microgram per liter of geosmin. If the 5 milligram of activated, so this is a contaminant, and we have added 5 milligram of activated carbon in 500 ml of sample. What fraction of they are asking that uh, how much this contaminant will be removed? Just ignore this part. See the random number. Okay, na. And it is saying that the adsorption, the removal process which follow the mechanism behind the removal process follow Freundlich isotherm, whose equation is given by QE kf into CE की power n, where n is 1.075 and kf is 0.45. You can look at the unit, and you have to find the equilibrium concentration. Or you have to find the percentage of how much fraction of geosmin has been removed. So for hint, I will give you one thing, that it's simpler version we have solved it. So we know that QE will be given by kf into C की power n, and we also know there is one more formula of QE. So we can equate this equation and we can find out CE. So this was just a hint that you have to find out CE. Please solve this question. It's I will give you 2 to 3 minutes, and this will require. See how you respond to this question. Then I will be I will be giving you this more question, or else I won't entertain more. I will be just recapping as usual. I think in this session I have realized that other method was good, where I will recap. Then based on the recap, these question were mostly based on the whatever I will recap, and in that case people used to participate. But I think this is the first time no one has participated in any kind of question and answer. All 8 question or 10 question were was being solved by me. Okay, the sorry, the see, you we have two formula. uh where did it go? Huh. There is one formula of QE, that is KF into CE into CE power n, and then there is another formula of QE that we know, and that is this formula. This formula, that is QE is equal to CI minus CE into V by M. For our question, CI is given, that is how much CI is given? 5, I think 5 microgram, 10 microgram per liter. Okay na. Then 10 microgram. You have to find CE. Volume is also given, that is 100 ml, and mass is also given, that is 5 milligram per liter. You can see everything is given to you. Sorry, volume is 500 ml and 5e. In this equation, what will happen, that I will put QE, that is KF into 1.75. Sorry, that is 0.45, and CE we have to find, and the N will be 1.075. It will be put here. Okay, and what we will do, that Q, that is also QE, but I have written just Q. Those equation will be matched, and we will solve it for CE. You can see that for solving this I have used Excel. Sorry, I have used Excel here. This question was from my, when I was doing my masters. This question was asked to solve in one of the Qs or one of the exam. So here you can see that first equation will be QE will be 0.5 into CE की power 1.0 n, and then we already know the second equation, and that is from uh, uh, where does it go? uh, Here you can, here we can see that it's not written directly. It's like It's in mixed form, but I can reorganize. But I will just show you here only. Okay, na? So what happened that the first equation was this, second equation was this. That is Q is equal to initial concentration is 5 minus C, which I have to find. Volume was V, that is 0.5 ml, zero point 0.5 liter, 500 ml was it was then 0.5 ml, and M was the mass. Okay, na? Then both were equated, and you will get uh, 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 where does it go? Huh. You will get a you will get a what will you will get a miss polynomial equation in the of power 0.45, and if you solve it you will get some value of Ce. If you get the value of Ce, see actually when the initial concentration is 10 milligram per liter, then Ce will come out to be 1.7, and you have to report your answer in fraction. Then initial concentration was 11 milligram microgram per liter. Final concentration is 1.77. Then uh, here you can see that removal efficiency is 83.9%. I hope you have understood it. See, I will ask again. I have also asked in the last class that please come prepare, or else you might think I'm just doing anything. I'm Anyone have any kind of doubt? See, most of the problem which will be coming to in your exam, in your assessment, have already shown you, but there are some few points. I will just go through the recap process. We have explained this thing, concept of ion exchange. So I think this is not a way of problem solving session where I will be just speaking everything. From I think actually one mistake which I did, that I prepared less content thinking that everyone will be participating. But from next time I will make sure that I have more content. Instead of 10 question I have more questions. Okay, then in case of an exchange we have already talked it for this. If you have any particular doubt, you can always ask. As I already said that in at the end of the session, actually, if you just look at the problem, if you are looking for the solving session is over. Currently, I have no more questions. Okay, na. So I request you to please say something. Say ask for particular doubts or anything. Okay, so now this thing is very common. We have batch process, then continuous process. What happen here that in batch we treat our water. There is no pain here. We treat water in batch. Water is contaminated water is added in one system, and it is done in that container, and it is we get filtered or treated water. But in continuous mode there is a continuous supply of the water. Okay, now so this is a basic difference between one is done in a single system, and there is no movement of water. After complete treatment it will be passed to the next unit, but here there will be continuous supply. This thing is a continuous supply. Here you can see they have used this ion exchange there. Here continuously their hard water is being fed to this ion exchange column, and we are getting this soft water. But in batch process you can see that only for a there is no continuous flow, and here you can see that a small volume of water can be treated. Then so this is what I was saying. Geolites, okay, now are the microporous crystalline alum. Oh no, it's not for aluminum. It's contain. aluminosilicates. Okay, na. Oh, it is usually. Sorry, I was right. This zeolites contains high amount of sodium, so this is generally used in the case of calcium. Okay, na. Used for water softening and ammonium ion removal. This is another thing. So type of resin. See, this was a question. This was also a question from your in problem solving that which kind of what are the characteristics of different kind of resins. Then here you can see that I think everyone should have idea of this. What do we call table that if we have a strong acid cation exchange resin to a strong and highly ionized in both acid and salt over this is very active over entire. Then we have weak acid cation exchange, a strong base anion exchange, weak base anion exchange, heavy metal selective chelating reagent. So this is also chelating reagent is generally used for also used for magnesium and calcium also. What happened that this EDTA has this calcium has more affinity towards this EDTA. So if we add calcium in this water, what will happen that this sodium will be replaced by calcium, and what will happen that we can treat our hard water. These are some of the exchange here. This is simple process like what I was saying that this is our zeolites. We are passing calcium magnesium. What will happen that all will get trapped here, and in the treated water will have low calcium, low magnesium and low iron, and we will that water will also contain high amount of sodium. And if you look at the drinking water limit or see, then there is no limit of sodium. And if you are looking in the industrial waste also, as we are talking about industrial waste, then there also the presence of sodium does not cause any kind of problem. Then this is the capacity. This is normal synthetic. Again, here is some common terms here. The concept, if you remember, we said that equal mole of acid react with equal molar of equivalent of this thing. This is another thing. One equivalent per meter cube for CSO3 50 gram CSO3 per meter square. There was one operating capacity which we have talked. Operating capacity is a measure of useful performance obtained with the ion exchange material when it is operating in column under a prescribed set of reaction, and it is given by number of equimoles of ion interest applied by resin volume. Okay, now minus this is another thing. Oh, this was the question which we have solved also. Here you can see that hardness of the water is this was normal question. Same question with different data. 100 liter of water was softened by an exchange regeneration. Itna liter of 0.1 normal HCl and NOH was used. Again here you can see that uh, amount of alkalinity is equal to amount of hardness water. This statement you can get it from here. Somewhere it has been mentioned. In general, the capacity is not written, but you should know. And this can be proved also that why equal mole of this amount of acid or alkalinity used to regenerate is equal to the hardness of the water. Okay, na? Then here we can see that 100 liter of water this much, then 150 into 0.1 of one normal HCl, then 15 liter of one normal. This is 50 equivalent of carbonate. We know the equivalent of carbonate, then we will multiply it by the this weight of equivalent weight of CSU3, that is 15 into 50, then 750, and then we know the volume. Then we will have 0.7 gram CSO3, and that then we can convert into equivalent, and from here we can say that it is 750 milligram per liter of, or milligram per liter as CSO3. Remember, it will, as we are converting everything in the term of CSO3, then it will be 750 milligram per liter as CSO3. Then we have this thing. Remember this is very interesting thing you should know, and many questions are asked. I think I don't remember anyone is preparing for GATE exam. I want to know from, like, are you guys a student or some professional work or researcher? You can introduce yourself. We are very limited number because currently I have assumed many things. Everyone know something. Anyone I'm faculty. Oh, good. Others? What about others? Your faculty from which college or which university?
Myself, Dr. M.S. Pradeep Kumar Patnaik
Hmm.
from Geetam University.
Okay, sir. Then I think you are senior than me also.
No, no, I want to get some information regarding this topic, so I enrolled for NPTL.
Okay. Means I was saying that you are senior to me also, but I'm just
Yeah, of
telling.
course, but in learning, everybody is a student, right?
Yeah, yeah, that is true.
Yeah,
Okay,
okay,
thank
thank
you
you.
for the session. What about others? I'm assistant manager working at course. I'm a student in Sarda University. Okay, good to know. So I will request from next one time come with the question, like, see, like, I will tell you the reality what happened. I have been given for each, there are 12 session, I have been given 10 sets of question, and even they said that finish the, you take your time and make sure that all the questions are solved. And if you look the um the is how toughness of the question, they are very easy questions. So if I start like, what do I call, if I start discussing those three simple topics, then it will be like it will be like I am just wasting your times also, my times also. So come from next time, please come with some questions, like then we can have a proper discussion. And see, before coming to the session, I make sure that whatever the topic is there, I have like I have gone through it, and I have collected some information that I will be speaking those things. So I come here with some background, expecting that there will be some questions from you, but it feel very disappointed that no one asked any question. But for today's session, it is okay. But if you are joining my session for next time, I see, like, this is expected. No one wants that. No one, it don't feel good. Like sometimes it's like, sometime in the middle of session I feel that I'm not able to convey my message in a better way. That's why you guys are not asking any question. And this is not just here, everywhere you go, always make a two-way communication path. Convey your message in a such a way that the person who is listening is able to understand you, and they can raise you some question. Like, I hope you are getting what I'm saying. And so right now, what I'm doing, that I'm done with the problem solving, and I have to be here till, I have to here till 8 p.m. That's why I am discussing, and I don't miss. I don't know whether I'm doing okay or not. That is also a problem. Thank you for your comments that you have given, sir. So this was all about ion exchange chemistry. Then different uh, we have different, there is one more question related to this topic, this k, just let me get that question, if I have that question or not. I will just, these are my mtech question, huh? This question is there. This is related to industrial, as we are working in the industry. I hope you are able to see the question. I don't. I hope that it is visual, not in a it is very small. A wastewater sample from factory contains 96 gram per liter of cadmium and X here is 16. Actually, in our IT, generally whenever professor gives some question, every person has different numerical value. Okay, now so there is no cheating and all this thing. So they give this type of question. So wastewater contains X this much of calcium. The sample is passed through an ion exchange reagent which was originally supersaturated with K. Okay, na. Now in your system already, like if we look into this, sorry, where did it go? Your reagent here in the in if we look at this expression, in reagent we have calcium, potassium. Okay, na, and as a absorbent, where did am I at correct? Huh? I don't think I am at correct slide. Huh? This is the reaction. Here it is saying that our system contain high amount of potassium. High amount of potassium. Where does it go? High amount of potassium, and we have to treat cadmium. Okay, now the sample is passed through the reagent that was saturated with K. So what will happen that this cadmium will replace potassium. Find the distribution of cations over the reagent milli when the equilibrium with effluent means, like you have to find the distribution of cation over reagent means we have to find this thing, concentration of R dash B. Okay, na, R dash B. Some of the information which is given to you is the cation exchange capacity of the reagent is 6 milli equivalent per gram. They have given you this equivalent capacity. This Kx is 0.86 gram per liter. Atomic weight is given to you, and you have to find this thing. Okay, na, this concentration of Rxb dash Rx R minus cadmium means what will be the concentration of cadmium in the reagent. Question is very simple. No, you have to just separate. Here they have done something different. Here the see this. They have given you this thing also, exchange capacity, that is 6 milli equivalent per gram. As we have less time, I will just directly solve it. Okay, now then see, first tell me, are you able to see my screen? I hope this Excel is not very small to you, looking very small to you. I'm assuming that it is visual. Okay, so here you can see this, we have already, now see here, first you have to write the equation, then you have to balance it. It was directly written, but if you see that our reactant will contain calcium, potassium, and uh, uh, this cadmium will be getting attached to this thing. So to balance the balance charge, see this will be now new this ion exchange will, this reagent will contain no charge now. So here we will have potassium. Now as here we have two uh, two positive charge on the reactant side, that's why we have added two potassium. And again chargeless thing. Okay, na, there is no charge on this thing, but as here we have two potassium, that's why we have added two. the, when we are writing any equation in ion exchange, we have to make sure that we are writing expression in a better way, because this we know that when we are writing reaction constant, then reaction constant depend upon the stoichiometry of the reactant and product. If the stoichiometry is not properly written, then you will be in you will get wrong answer. Okay, so now here it is this thing, equilibrium we have this equation. See, it's look like simple. You can see that this to write this equation, we were given 1 marks, and trust me, many students were not able to write this equation correctly, and they end up in getting very even less marks. Then based on this thing, we can write k reaction constant, that is product um, product divided by reactant. Okay, then we have first thing. Okay, now then it is saying that there is one thing, exchange capacity was given to you. See, the exchange capacity. Exchange capacity of the resin is 6 milligram per liter. 6 milli equivalent per liter. Now what is happened that this exchange capacity in simple terms can be also referred as the concentration in the uh, it is the like ratio of this thing, ratio of exchange capacity. You can like what is the, how do we define exchange capacity in a simple word? It's the simple the ratio of different ion in ratio of different ions. Just look at the formula. I hope I'm not able to explain it, but you can see this expression. Here is the ratio of cation in the per the exchange capacity is given by the ratio of this cation per how much resin is there, and plus the uh, contaminant concentration plus the how much resin is there, and that is given as 6 millimolar per milli equivalent per gram. The concentration is already given to you, k plus is given to you, and cadmium plus is also given to you. Okay, now sorry, I think I have spoken something wrong. Huh. How exchange capacity is simply defined as how much cation is exchanged to how much reactant, and how much pollutant, that is cadmium, is attached to this your resin, that is your SURF is surfactant, means part of resin where this cation and NI are present. Okay, then the summation of both contaminant, that is here cadmium is contaminant, and the ion which will be exchanged, summation of both is known as this thing, uh, exchange capacity. You know the cadmium calcium potassium concentration, cadmium concentration, and we know this equation. In this equation, now we will doing that we will be putting this cadmium concentration and potassium concentration. We will have to, then we will have this kind of equation. Okay, now that is cadmium divided by potassium square will be 8.755, and you know the potassium plus cadmium is 6 milli equivalent per then we will solve this equation, and from here we will be finding the concentration of, and we were asked to find the concentration of this cadmium attached to the surfactant, that is how much finally when after treatment how much cadmium has been removed, or how much cadmium is there attached to the resins. This was simple question. This was question similar to this thing only. Instead of asking this xa and xb, they have asked you to find r minus means this how much contaminant has been get removed, how much contaminant has been attached in the resin. Okay, now I hope you are miss I miss, and the only new thing here was that this CEC, that is exchange capacity, cation, this thing cation exchange capacity. With time I have also forgotten it, but this is how cation exchange capacity is defined. That summation of this thing, summation of um, summation of concentration of contaminant on surfactant plus concentration of ions in the surfactants, and you were was asked to the concentration of cation over the resin. I think that's all for today. It's already 7:55, 7:45, 55. So, anyone have any question? First of all, tell me, will you are you miss, did you able to get this question, and if this similar question will come again, will you able to solve it? This is another thing. I hope so. That another, I will give you one question for this thing. What do we call it? There is one more question. So just take a screenshot of this question and try to solve it. It is little bit, but it's same thing. It's related to adsorption, not related to this thing. But if you recall the formula, where if you have see it's little bit how I can say, just take a screenshot of this question. I won't be explaining you but the concept is similar. Here you have to use the Freundlich isotherm, and you have to find CE and all this thing. And the challenge of this question is that you have to find how much volume of the water has been treated, and you for X you can use 14. That's all for today. I hope from next time there will be two-way communication, or else other option I have that learning from, I think learning from this session is that I have to come up with more materials. So I will try to get more questions from, because from NPTEL team I have been given only 10 questions. But from next session of course I will be coming up with more questions, so that I miss, somehow I did not detour from, because this is problem solving and we have to solve the problem. Okay, if no doubts, then I will be ending the meeting for all. Any question? No question, then thank you for joining, and I request you to everyone, please join my next session also, that is on next Tuesday. That's all for the, let me see any message. No message. Okay, thank you all for joining, and that's all for today.